right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Someone's coming in. Let them in here. Let's jump into it. Let's make sure I can see the chat here. Okay, awesome. So we are back. Recap of what we did last time. Let's see. We were talking about continuity, and we did some examples of how we would show that something was continuous or not, determine where it would occur. So we did some examples. Let me just go over some other ones. So we learned, one thing we did learn is about the elementary continuous functions the time before last time, those 6 functions that are continuous on their domain, that moving forward, you can allow yourself to assume this. And so that allows you to attack these continuity problems more efficiently, because now, instead of trying to worrying about every possible real number, you can end up worrying about only a few, 1 or 2 or 3 of them, right? So give you a function like here, ask you, where is this continuous? There are certain things you can know that will tell you I'm allowed to ignore a bunch of numbers and just focus on a few. So in the case of piecewise functions, you focus on the pieces that the function is broken up about. So in this case, of course, it's obviously different for x equals 2 than otherwise, and so that gives you the fact that x equals 2 is a value you really need to pay attention to, because on the left and the right and at 2, things might behave differently. Then when you look at each piece, you'd realize that these are some of the elementary functions. So the top one, the x squared minus 4 over x minus 2, that is a rational function. We know that's continuous on its domain, which means as long as the denominator is not 0, that is fine. And so we know as long as we're not 2, we're actually okay in the first line. The second line is 0. 0 is an example of a polynomial. Those guys are continuous everywhere. So we also know that that guy is fine no matter what happens, right? So then we realize that x equals 2 is really the only thing that we should be concerned with. Everywhere else, we're actually fine, right? So step 1 would be to identify the potential problems and make sure that you deal with them. So here we know that if x is not equal to 2, we're continuous, everything is fine. However, at 2 is what we're concerned about. So now we go to at 2. And we learned the 3 things that we need to check for continuity. We need to check that the function is defined, that the limit exists, and that the limit equals the value of the function at the point of interest. So that's what we did. Is the function defined? Yes, it is 0, because by definition, it tells us when x equals 2, it is 0. Does the limit exist? Now remember, the limit doesn't care about being at 2, so you would ignore the second line, and your limit would deal with the first line. So we would find that limit, which now the limit strategies that I taught you guys a couple of classes ago would come into effect, and you'll find the limit that way. Then you just check that these two give you the same answer, and in this case, they did not, which means your function was not continuous at that value, which means in general, you're continuous except for that value, because we already determined that if x was not 2, everything was fine. Here at 2, we have a problem. So in general, this function is continuous if we're not at 2. That being said, and we actually saw why that happened. There was a hole, and someone where it was their one job to fill in that hole, they did it incorrectly. But we also had an important note that was brought up by a question, I think by James, that, is the function above continuous? Can I say it's continuous? And the answer is no, because the definition of just continuous period is that you are continuous for every point in your domain. X equals 2 is in the domain of this function. At x equals 2, it gives me a value. However, we're not continuous at 2. Therefore, I cannot call this a continuous function. It's not a continuous function because there are points in its domain where there's a disruption there, right? So in general, it's not continuous, but I can tell you specifically where it is continuous. It's continuous on this interval specifically. But in general, it is not a continuous function. It's not of the same class as the 6 continuous functions that I mentioned earlier. So now we have 2 last examples to go into before we get into the main topic of discussion. And so hopefully we can go a little bit quicker with these because we now know the main ideas and we just recapped them. So Examples we had to finish last time are these two, D and E. So let's begin. Let's start with D. So here's a function. It's actually very similar to the previous example. Where is it continuous? So here is what a fully worked out answer would look like if I gave you this problem on a test or a quiz or something, and I required that you showed your work. I probably expect you to write it out this way. So for one, I want to make sure that you are knowing what the problem spots are and what the problem spots aren't. So you should have a statement that lets me know that I'm not ignoring everything, I'm considering everything, right? So you should start with saying, well, if x is not equal to 2, we're fine, right? Now, you don't have to justify that, as I've been saying, because that's actually you applying the concept of what an elementary continuous function is, and justifying that would look something like this, which I don't want you to have to go through. Right? Justifying that would look something like you just pretending, oh, we're looking at some random value A, which happens to not be 2. And then you have to go and in general prove that for any A not equal to 2, this is going to work and blah, blah, blah. But I don't want you to have to waste time doing that because then that's like you having to do 2 sets of problems. So at this point, though, however, at the same time, by the same token, I don't want you to not be considering that in the first place. So just write a sentence to let me know you actually consider it. I identify that 2 is the only problem I have to worry about. If we're not at 2, we're fine, right? So just make a statement that tells me that you realize that, right? As opposed to you thinking that 2 was the only thing you had to worry about and you didn't consider anything else, which is not what you want to do, right? So I want to know that you considered everything else. So you're going to write down this, if x is not 2, we're fine, right? Because each of these guys individually work. The top one is a rational function. The bottom one is a polynomial. The rational function works as long as we're not 2. And in the top line, we're told that x is not 2, so it's fine. And in the bottom, it's a polynomial. It's literally fine anywhere. So everything is fine. We're hunky-dory if x is not 2. So now at 2 is what I care about. That one I have to do a little bit more carefully. So now what I'm going to do is I'm going to note, you don't have to write note, I guess. F of 2 equals 4. So that's from the definition. So F of 2 defined. Boom, 1 check is done. Okay, awesome. 2, now I'm going to find the limit as x approaches 2 of our function. And what is that? You need to identify where the limit actually, which function you're taking the limit of. And because you understand how limits work and limits don't care about being at 2, but rather being close to 2, you know you're going to take the limit of the top function. You're going to go through the limit strategies to know that strategy 2 is going to work here. So you're going to get that answer is 4. So now you know the limit exists. 3, now you're going to check. Check 1 and 2. Notice that for the limit, which is right above, I got the answer 4. This is actually equal to the value of the function at 2. And so that checks out. Therefore, I can conclude f is continuous where? What can I conclude from this?
It's continuous everywhere.
Well, from my immediate calculations, I can't conclude that because I'm within the second bullet point here. So there's a bullet point here and then there's a bullet point here. So I'm still within the second bullet point.
Oh, so then it's continuous at 2?
So I can say it's continuous at 2. And then finally, I can make the general conclusion, right? So this means that f is continuous everywhere. Right? Because we're fine at x equals 2 and also at x not equal 2, right? So we're fine if it's 2, we're fine if it's not 2, we're fine everywhere, we're fine in general, right? So it turns out that, by the way, this is a continuous function. Like continuous function in general. Because its domain is all real numbers and it's i.e. continuous on its domain. Its domain is all real numbers and it's continuous for all real numbers. So yeah, that's cool. Yeah, so that's essentially what a fully worked out problem would actually look like for this example, right? So you'd basically say, well, at 2, if we're not at 2, we're fine, everything's good, right? So you don't have to justify that, but I need to know that you considered it. Then you say, okay, my only potential problem spots is 2 itself at x equals 2. Then check that the function is defined, check that the limit exists, check that they give you the same value. If any one of these guys don't work out, it's not continuous at 2. Then you can make a final conclusion. So by going through this, we realize that it was continuous at 2, and so yeah, we're good. So so again, what happened here is that we had this situation where at 2, there was potentially a problem, but someone filled it in, right? And so now it's continuous. I can literally draw this without lifting my pencil on the page. There is no difference between this piecewise function and the actual line itself, the line y equals x plus 2. There's no difference now, right? It's a continuous function just as continuous as x plus 2, right? So someone actually filled it in the right spot, right? So yeah, now it's continuous. Let's move on to the next example. It's going to be the same kind of idea. So here I'd realize that if x not equal to -2, we're fine. The top line only would have a problem if x is equal to -2, you divide by 0, but we're told that we're not at -2, so that guy's just a rational function and they're continuous on their domain, so he's actually fine everywhere. The bottom line is 1, y equals 1 is a polynomial, so that's fine no matter what. So as long as x is not equal to -2, we're fine. So now I just go to at -2. 1, what is the value of the function? F of -2. Well, if I look at the definition, it is 1. So 2, find the limit as x approaches -2 of f of x. That is going to be the limit of that part. How do I find that limit?
You could simplify the top version.
Can simplify the top. It actually factors, right? So that would be 3 into 2, it looks like. think that's a delivery. Yeah. And you actually get the value 1 here. So 3, now you check the limit as x approaches -2 of f of x is 1. Is that equal to the other guy? Yeah, it's actually equal to f of -2. So this means f is continuous at x equals -2, and this means f is continuous on the entire real line. It's continuous at -2. So it's continuous on the entire real line. So in fact, there's no difference between this function and the line y equals x plus 3, right? It's like the line y equals x plus 3, but it had a hole when x was -2, but we filled in that hole and we filled it in the right spot. So we're good. So now, remember you guys have a test this week. Not a test, a quiz this weekend. So I just, want to make sure, and you'll get practice working on problems like this in the homework, I think, and also in the actual textbook. But there are different problem types that I could ask of this type. So I just want to mention those so you can be prepared. Other problem types. So for example, I could have asked so let me give you this function again. X squared plus 5x plus k over x plus 2 if x is not equal to 2, and it's 1 if x equals to 2. And I could have asked, what must k be so that f is continuous everywhere, right? So I can ask that question, or I could have done it a different way. I could say the f was x squared plus 5x plus 6 over x plus 2 if my x is not -2. And it could be 1 if your x is -2. Right? Or I could put the k down here. I could put k here and ask the same question. Right? So I can actually make parts of the problem actually disappear. And then I ask you to figure out what would that have to be to get certain things to work out. So that could be a problem type that you'll see. Also problem types like maybe, let's see. F of x equals, let's see. Say a minus x if and then I can do something like x plus b. Let's see, what would be a nice one? Say if x is less than or equal to 2, and this one if x is greater than 2. And I can ask, what does, I don't know, I'm making up a random value, so it probably doesn't have an answer. I think it has an answer though. Find values a, b that would make f continuous everywhere. Or justify why no such A and B exist. Right, so that's another kind of problem type. This one is a little bit more involved and challenging, but I guess we could quickly solve it. So here the answer would look like the following. So you would say if x not equal to 2, we're fine, right? How do I know? Because each individual is a polynomial. They are fine no matter what. So as long as we're not at 2 itself, we're fine. Why is 2 an issue? Well, on the left of 2 and the right of 2, we have different behaviors. It's possible that there's a disconnection because of how these things are defined. So at 2 is a concern, right? However, if we're not at 2, each of these guys individually will work out fine because they would represent polynomials when A and B is just a number. So how would you actually figure out what do these guys have to be? Well, you need to force the situation that causes continuity at 2. It means you need the value of the function to be equal to the limit at that point. So how would you go about doing that? So at 2, for continuity, we need f of 2 exists, limit as x approaches 2 of f of x defined, and both values equal, right? Okay, so here what you can do is you tackle the first one and you say, what is f of 2? Well, f of 2 is actually going to be equal to, notice that here is the line that corresponds to being equal to 2. So I would just plug in 2 right there. F of 2 is a minus 2. Now I don't know what a is, but I know that's going to be the expression. Then I'm going to talk about what is the limit as x approaches 2. Okay, now if I were to ask you, what is the limit as we approach 2 of this expression, how would you go about doing that?
We should use like one-sided limits.
One side at a time, right? Because now you're like, it's a different thing on the left and the right. So for this part, right, you need the one-sided limits. Well, what if, well, it would depend. Are we approaching 2 from the left or the right? Okay, and so as we approach from the left, who are we looking at? What is the function we put here?
A minus x.
A minus x. So you'd put a minus x in this position. And for the other position, you would put the other function, x plus b. So for the left part, you would put actually the x plus b. So now this is actually going to be equal to, well, a minus 2. And this part is going to be equal to b plus 2. So here what you would get is we need okay, so here you're going to be like, well, we need, you know, a minus 2 to equal to b plus 2. And yeah, I'm just realizing that for a class like this, I probably wouldn't have that many unknowns, because ultimately what we can do here is just have one equation with 2 unknowns. And so that's kind of weird. So let's modify this a little bit. to make things a little bit clearer. So let's say whatever, it's when x equals 2, it's 0. Just change this a little bit to get a nice answer. Okay, so that's what we need, right? So we need that to be true. So ultimately we need all of these guys to give us the same answer. So the 0, which is the answer in part A, needs to be equal to A minus 2, also needs to be equal to B plus 2. So this means that I need A minus 2 to equal 0, so my A must be 2. And I also need that B plus 2 to be equal to 0, so my B must be minus 2. And that would be the answer, right? So you can actually modify questions like this to kind of test more conceptual understanding of the process. So if I put in unknowns in this situation, like I don't even tell you what all the real numbers really are, you should be able to, just by forcing certain conditions to happen, you know that the value in the of the function, what is defined, needs to be equal to the limit. But in this case, I need a one-sided limit. So I need the value of the function to equal to the value of the limit coming from the left, equal to the value of the limit coming from the right. And by me setting up that idea, I'm able to solve for the variables, right? But that's like, you wouldn't know to do that unless you understood the concept of what do I need to be equal to what? How do I set up the limits? What function do I look at when I'm looking at what limit, right? So there are all these things that could happen, right? So yeah, so you can see problems like that. But for now, what I want to do is to actually move on to something interesting. We are going to start talking about why we need this stuff. So let's actually do this. We're going to attack the rate problem. Remember, it's one of the main kinds of problems that calculus was invented to solve. We're now going to solve this in Calc 1. So in order to actually do that, there is a motivating example that I want to talk about. And I think I put it here somewhere, or did I? Did I not? Did I leave it in the last one? I know I typed it somewhere. Maybe I typed it in the other class? Yeah, they're over here. Okay. Let's copy these over. I don't think I'm going to need beyond that at the moment. Because I knew I typed this up somewhere. Okay, let's see. Let's copy these guys. Oh, I did actually type it up, but maybe I did it. No. Yeah. Oh, this is misbehaving. Is it going to remember the thing I copied now? I don't know. Let's see. Let's hope for the best. Yes, okay. Attacking the rate problem. Okay, so what we're going to do first is an example that hopefully you will find enlightening and motivating. Okay, so we're going to attack the rate problem. Suppose you're tracking the distance traveled by some moving object, and let's assume for the sake of argument, this object is moving at constant speed. So not speeding up, it's not slowing down, it's just going, like a thought experiment. Let's say you had nothing to do with your Friday afternoon, so you watched this thing for like 3 hours, and it traveled 150 miles in that time, right? So let's actually try to analyze this situation, right? So you're tracking some object over a 3-hour time period. It's not speeding up, not slowing down, so it's moving at constant speed. And you are going to analyze that. So here, let's graph the distance traveled by the object versus time. So here, A. Of course, what would this look like? So here's distance. Here's time. So the object is just moving. So there's, of course, time equals 0 at some point, where you can just assume the distance is 0. At time 0, distance covered 0. Now, at some point later, so this is time in hours, at some point later, you're like, okay, 3 hours later, you go back and you realize, hey, this guy actually traveled the distance of 150 miles. Right, so it ended up here, right? Now I want to graph the distance traveled. Now, because this thing is moving at a constant rate, it's not speeding up or slowing down. There's no place in which it covers a lot more distance and then it doesn't cover a lot more in the other thing. And so it doesn't do that. It actually is going to move like, it's actually going to move like a straight line. Right? So the distance traveled, the distance graph would look like this. It's just a straight line segment. Okay, now I asked a very leading question. Your Honor, he's leading the witness. Okay, what is the slope of this graph, right? So B, how do you go about finding the slope?
Change in y over change in x.
Change in y over changing x. With here, you can see it's going to be, if you can label it, but yeah, it's delta y over delta x. So the y value is changed by 150, the x value is changed by 3, so it's 50, right? C. Interpret your answer to B, right? So in B, I just found that the slope was 50. Interpret that value for me. What does the 50 mean in this context?
The object moves 50 miles an hour.
50 miles an hour. Notice here, we have change in y over change in x. This guy here was measured in miles. This guy here was measured in hours, right? So this means the slope was actually 150 miles per 3 hours. And in other words, when I simplified it to 50, I had 50 miles per 1 hour. Or in other words, that's 50 miles per hour. So here, the slope is actually equivalent to how fast it's moving. Okay? And that's the main idea. Slope can be considered something that we call, quote unquote, rate of change, right? The slope is not just this thing that tells you how tilted a straight line is. However, if we start to label what the y-axis is and what the x-axis is, you can actually think of slope of a line as how fast is the dependent variable changing with respect to the independent variable. This is basically telling you every time the hour changes by 1, the distance changes by 50. In other words, the distance is changing 50 times as fast as the time is changing. We represent this by a speed, miles per hour. It changes 50 miles for every 1 hour. This is how fast it's moving, right? So in other words, slope is synonymous with speed, or in this case, technically velocity, but we'll get to the distinction later. But that's the thing I want to do. So this is the motivating example. So in a very simple idealistic case where nothing is speeding up, nothing is slowing down, it's very easy to track everything. I have my nice stopwatch. Everything is like, boom, perfect. I know what's going on. I know how fast this thing is moving by measuring one variable, how it relates to another variable. So time is my independent variable. Time is just going, and I'm tracking another variable. So it's like I'm tracking a function over time, right? Time is like my x, distance is my y. So I have some function. The function happens to be a straight line. The slope of that line can be interpreted as speed, how fast it's moving, right? Okay, so now the question is, can we generalize this? Right? Which is always the question that math people ask. Like, how can I get this knowledge that I know about to apply to a wider, a broader situation? Right? So now, suppose it's not changing at constant speed. Right? So this is an object that it's slowing down, it's speeding up. So if you go back to like the example I did from the class where I was explaining what calculus is about, could be the tides. Sometimes the tides is rising, sometimes it's falling. It's not always doing the same thing, right? So this is a more complicated scenario, right? So now I just want to talk about some random thing that I want to know how fast it's moving. And let's say I can actually track it by some axes, right? So here again, y is the distance, x is the time, right? But now the function is some random curve. And again, not super complicated. I just made a very smooth changing curve here. So what if we wanted to find the speed of an object at a specific instant, right? So obviously this thing has no slope in general, but maybe like, let's say there was a point here. I'm interested in knowing how fast the object is moving here. Right now, at this instant, how fast is it moving, right? This guy was always moving at the same speed. The whole time it was moving at 50 miles per hour. But now things are changing. How it's speeding up or slowing down is changing. So I can't just say it's always moving at 50 miles an hour. I have to say, well, at this point in time, it was moving this fast. At this point in time, it was moving this fast. So now how to actually answer that question? This is actually is equivalent to answering the rate problem. Some random thing is moving. I want to know how fast it's moving at every instant, right? So now The thing is, we know how to deal with the simpler situation. The idea is, how do I get this to match the simpler situation, right? So here's how. So the question is, can we generalize this? The answer is actually yes, otherwise we wouldn't be here. So the idea is yes. We'll use the idea above. What is that idea? Well, the idea that slope measures speed. So now to find the speed at this point, in other words, what I want to do is we need the slope at this point. So now the question is, how do we find the slope of a curve? Right? We know how to find the slope of a straight line, but this isn't a straight line. This is a curve. How do we find the slope of a curve? The answer, surprisingly, think like a flat earther, right? So, which turns out that was actually how we're going to do this. The idea is, yeah, it looks curved right now, but that's because the scale at which I'm looking at it. You see, there's another scale in which it would look very flat, right? Which is why some people believe in a flat earth, right? If I were to zoom in on this, so I zoom in, then the curve actually looks a lot flatter, right? Kind of like a line, right? So people look around, well, the earth looks flat. I guess it's flat. Yeah, but it's on the, you're zoomed in. The earth is huge and you're this small. Yeah, it's going to look flat to you, but really it's curved. So that's the idea. The idea is to have a curve, but look at it on a scale where it looks like a line. And so now what you can do is but which line? Let's create a line to approximate the curve at this point. Okay, so what I'm going to do is I'm going to take this zoomed in picture of where my curve is almost flat. Here's the point I care about. What I'm going to want to do now is create an actually flat straight line. So we create a line that passes through that point and gets closer and closer to what the curve does, or it's actually the other way around. To approximate the curve. In the sense, the more we zoom in, the closer the curve conforms to the line. A line that does this approximates the curve to the at a point is called a tangent line. So the word tangent means to touch, touches it in this one point and it approximates it. You don't have to touch it in one point locally, technically. I don't want to get into that right now, but that's what we're going to do. The idea is I know how to measure the slope of a line. So if I want to measure the slope of a curve, I'm just going to use my knowledge of how to measure the slope of a line. And so what line would I use? Well, the idea is if I zoom in far enough, this curve is going to apparently start to flatten out by relation. So find a line that kind of matches how the slope is behaving when it's flattening out. And so that line is called the tangent line. So it turns out to find how fast this object is moving, all I need to do is find the slope of the curve. However, the slope of the curve can be approximated by the slope of this straight line. So now the problem becomes, it goes from how do I figure out how anything is moving to how do I figure out how fast this slope is moving to how do I figure out how fast this straight line is moving, to which the answer is slope. So now we've reduced the problem of the rate problem to how do we find the slope of this line, which is awesome because we know how to find the slope of a line. Issue though, how do we find the slope of the tangent line? We only have one point, right? We need 2 points to find the slope, right? You need y2 minus y1 over x2 minus x1. So I guess now we give up. We can't do it. We can't solve the problem. It's impossible because we only have 1 point. Of course, it's not impossible, right? Math people, what you do is when you figure out simple situations, you try to apply those situations to more complicated problems. So here's how we actually do it. Here's how to do it. Make up another point. Just make up another point. I don't know how else to say it. Make up another point. So what we're going to do is here is point I care about. So this is point I care about. Here, some other random point. Notice that I can actually connect those points with a line. We know that line already. We call that a secant line. And so I can actually measure the slope of that line. So we actually know how to do that. We actually did this already when we did average rate of change. So that's why that was handy. So let's actually do that here. Let's actually do that here and figure out. And then ultimately, we're going to be able to derive a formula that's going to solve the rate problem. And that guy is going to be the star of the show that we're going to do for now. So now the idea is, here is a point. Let me call that x, which means the corresponding point here is f of x. Here's some other point I just made up. I want to track it in terms of x, so I call it x plus h, where h is the distance between the points. And of course, that gives me f of x plus h. And we saw last time, the slope of the secant line is going to be f of x plus h minus f of x. over h. That's our distance, our difference quotient. Now, here's the idea. Light bulb. If we make h get close to 0, the 2 points become 1 by their powers combined. Right? So notice what you're going to have happen is that you have this curve, you have the tangent line that you care about, and then what you do is you have a point like here, and what you do is you kind of close the distance between the 2 points to the point where when the blue point is right on top of that point, so here is x, and here is x plus h, but my h is getting smaller. Right? And you'll notice that the blue line kind of changes over time to fit to the red line. So the blue lines converge, as we call it, to the red lines. Now the red line is the tangent line. The blue lines, these are secant lines. So it turns out that secant lines, I can make them become the tangent line. So now we're like, okay, so I can see as a picture what I want to do. I just want to make up some other fake point and close the distance between those 2 points. In other words, I have to take one point and I have to inch it closer and closer to something. But I can't let them actually be the same point because then I can't find the slope from that. So I want to get closer and closer to something in such a way that I can get as close as I want, but these cannot be the same. I don't want to be at this point. I want to get super close to that point. So I can have 2 points to get the formula I want to use, but at the same time, I want them to be so close to each other. So now we're like, do we know anything that we can get close to something without actually being there so that I can use 2 points that are effectively 1 point? Yes, limits. That's how we can do that. And so the math people thought, hey, let's invent something called the limit where we don't actually care about actually getting to the point. We care about getting close to the point. I'm like, what would such a thing look like? Well, that's what our last few classes was about. So we pause on this rate problem, we go and invent limits, and then we come back. And ultimately, this is what happens. The slope of the tangent line is going to be a limit. As I let the distance between these points go to 0 of the difference quotient. This limit is super important. It solves the rate problem. Which is a major problem, so we give it a name. We call it the derivative. Right. Or to be more specific, you have to take your glasses off and hopefully they're shades, and you go like, we call it the derivative. And then you walk out the frame, right? That's how you do it properly, right? Because this is major. This actually, with this limit, we can figure out how fast any random thing is moving. Can you track it by a function? I can tell you how fast it's moving. Rate problem solved. Now, of course, there are things, right? The limit doesn't always exist and blah, blah, blah. And so there are nuances to how to get this to work. But whenever this can work, we're golden. We've solved the rate problem. That's what's called the derivative. So that's the introduction to the derivative. Of course, we're going to actually put this formula into use the next time. And we'll stop right there. So I just introduced the derivative, and I'll just tell you the notation. We denote it by f prime of x or something like dy dx. So i.e., I just defined something for you that given a function f of x, how do you find the slope at any point of that function? You find something that's called f prime, the derivative, and it is the limit as h approaches 0 of f of x plus h minus f of x over h. Now that formula you have to know. So for your quiz, that's all you need to know for the quiz this week is what expression gives me the derivative. As far as applying that expression to doing stuff, we're going to do that next class. So yeah, we will stop there. But hopefully that was insightful and cool. I remember when I first found out how someone came up with derivative, I was like, what? That's crazy. Oh, I see how that's all. I was like totally enamored with this process. Like how you go from a situation that seems impossible to getting it to a situation that seems almost impossible. And then you deal with something easy, like finding the slope of a straight line to figure out this impossible situation. Yeah, you don't have 2 points, just make one up and make them close together. Right? That's just like, yeah. That's why math is fun, kids. It doesn't always seem like that in school, but yeah. Anyway, we will stop there. Hopefully that was cool. Thank you for your time and attention. And quiz this week, don't forget. And I will see you guys in the next one. Ciao.